It's our great pleasure and honor to have here with us Professor Abbadi from the University of California, Santa Barbara. And today he will be talking about a wake-up call databases in an untrusted universe. Professor Abbadi got his bachelor from the Alexandria University in Egypt. He completed his PhD in Cornell University many years ago. Since then, he had a vibrant career. Many awards, IEEE Fellow, ACM Fellow, Distinguished Award from the University of California for his mentorships to the 35 plus PhD students, yes. So, and you know, many younger scientists are looking up to his great academic career. It's our great pleasure and honor to have you here with us, and welcome.
Thank you. Thank you for inviting me. It's always a pleasure to come to Cyprus. Like Dimitri said, I just grew up, your neighbor, kind of. Alexandria is very close by. So I'm just curious, how many here are graduate students, masters or PhD students? Okay, so the rest of you are undergraduates. You've all done a database class? Yes, no? Yes, okay. If you've done databases, you know SQL? Okay, do you know what a transaction is? Okay. Okay, so let's, so this talk is actually an academic talk, so you'll have to stop me when things are not very clear. I've tried to tune it down, but we'll see how it goes. It does build on a lot of what I feel is very interesting and important foundational issues in distributed systems and database systems. So I work in the middle between the two. And I want to wake you up. I know it's early in the day, but also the talk is about working in an untrusted world. And that's the motivation for this talk, is that we have lived for a long time making certain assumptions about the underlying infrastructure, and now things are different. And we need to be worried about it. Maybe not immediately, but in the very near future. This is work with my colleague Divi Agrawal, we've been together for a long time, and we've been working together, and these are 3 students in my lab. So I'll start with a fairy tale. You know what a fairy tale is, yeah? So that's what they teach you in your undergraduate database classes. That the data is relational, it's structural, it has tables, everything, there are attributes, columns, rows, everything is very nice. There's a primary key, a unique primary key. This is the story that you hear. You are told that the data is clean when it has the data is from a certain domain. It all follows the same rules. If there is, my name is Abbadi, it will be written like I spell it everywhere, E-L space A-B-B-A-D-I. Last night when I checked into the hotel, they told me to get on the Wi-Fi, you need to just put your room number and your last name. I said, what's my last name? She said, she looked at me and said, you know your last name, here it is, Abbadi, E-L-A space A-B-B-A-D-I. I go to my room, I try E-L-A-B-B-A-D-I, it doesn't work. I try without a space, I try capital letter, lowercase, it doesn't work. Eventually I call and I say, something is wrong. They tell me, well, your last name is E-L-A-B, 1B, A-D-D, 2 Ds, I-P-R-O-F, professor. All of this is my last name. So this is how data is clean or dirty, actually. So you have the same information, but different people decide to put it differently for different reasons. Some of them are legitimate, some of them are mistakes. So data is clean, and this is not the topic of my talk today, but the infrastructure is sitting in a computer room, which is in the computer science department, and we know who is working there. Everything is trusted. Even when a failure happens, A failure is very well defined. It's either failed, crashed, the computer is down completely, or it's working. There are two modes only. And we know how to work with this. If it's down, I don't have to do anything. If it's up, I can do everything. Okay, this is not the truth. This is the end of the fairy tale. Really, the world is very different. So, data is not just relational data. It's not only structured. There is images, there are pictures, there are videos, there are all kinds of things. There are graphs, there are streams of data, all kinds of things. So we have to deal with all this. Like I told you, the data is dirty, actually. There are different versions of it, and we're doing joins on data that was created by different individuals, and they are not all connecting with each other. And from my point of view, what is very interesting is that the failures are not necessarily crash failures. They are not necessarily just benign, what's called fail stop, which is that the computer just goes down. It can be malicious. It can be what are sometimes called Byzantine failures, meaning that you could sometimes answer something and something else to another person. You might have a bug in your code. There are all kinds of reasons why the data can be, the infrastructure, I cannot trust it. And there are lots of different, it's been in the news a lot. We give our data to the cloud, we give it to Facebook, we give it to Google, we give it to Amazon, and we have breaches of the data. Sometimes the data that I have is taken over by somebody else. You have leakage of information, and what can be worse is that there's potentially hacking from within those systems. I do not necessarily trust who is there. I'm not saying I don't necessarily trust Amazon, but maybe there's an employee at Amazon who goes rogue. Maybe there is a piece of code that is put on AWS, on the infrastructure, in the cloud, that might be wrong. So there are all kinds of instances and circumstances in which this can happen. In fact, there was this article where James Clapper, was the FBI chief at the time, and he predicts that this is the future, is that we have to worry about data manipulation. So somebody goes in and changes a little bit of the data, and then you are stuck with data that you don't know, is it correct or is it not? In general, the data is in the cloud. Where is the cloud? Who has control of it? What is happening there? And I've been recently interested in blockchain. And in blockchain, many of you hear about Bitcoin. Who has the blockchain? Who has copies of the ledger where the information is? Anybody who wants to have a copy. Do we trust everybody? Not necessarily. And actually, blockchain and Bitcoin, in its design, make sure that it is tolerant to malicious behavior. So obviously, we have a big problem. We do not know how to deal with all these things. So what are we going to do? Luckily, we are not alone. There is a long history of people who have worked on particularly malicious types of failures. So there's a lot of work in the distributed systems community, and in the distributed systems community, there is the problem of Byzantine Agreement, which Lamport had proposed exactly 40 years ago in a few months. I think the paper was published in 1980, so it will be 40 years since then. So that was a problem where you want to have agreement among a set of processes that have potentially malicious or Byzantine failures. Who has heard about Byzantine Agreement here? Just to give me a sense. Okay, so this is, I'm going to work with this a little bit in the talk. So yeah, I'll need to give you some background information when it comes along. So there is the distributed systems community which has worked on this, but there's also a lot of work in cryptography and in security and privacy. The main challenge with both of these communities, but especially the crypto world, is that they've developed very, very strong and very good techniques, but they are usually very expensive. And I'm a database person. I worry about a lot of data. I worry about scale. And often these protocols are not designed for scale. They're designed for protection. And so there is a tension. And the best way to work on this is to work together with cryptographers and try to come up with compromises or ways in which to scale and yet protect what you're working on. We also have in our database community, we have data privacy work and especially the notion of transactions. So again, transactions are this very beautiful concept that was developed early on by the database community. And it's the idea that you can do your SQL operations, you're doing select and update. So you have read and write operations, but also you have update, multiples of them. I'm going to update the grade of every student in this class. I'm going to increase it by 5%. I have to do it for everybody. And I have to do it in an atomic manner. I have to do it in spite of the fact that there might be updates that are happening at the same time concurrently, or if there is a crash. And that is the traditional approach, to think of it as a crash. Even if there's a crash, it's either you get all the operations update to all the class or none of them. So that's the idea of, and this was developed by, again, one of the most, there was a team of people at IBM, but the most important person at the time was Jim Gray, who is one of our community also, who works on this topic. So let me give you a little bit of background about consensus, which is agreement, this idea of Byzantine agreement. So this is a thing, this is a topic that I would spend the whole 10 weeks discussing. So I can't give it all in one slide, but let me give you some basic ideas. One is that we assume the network, the distributed system, the network is either synchronous or asynchronous. If it's synchronous, it means I have some notion of a timeout. I know that there is a maximum amount of time in which a computer will respond and network delay across the network. So that's a nice system. If I have a synchronous system, then if I suspect that one of you is not alert, is not up, I can send them a ping message. And if I don't hear within a timeout, I can declare that site is done. In a more realistic environment, we assume an asynchronous system. An asynchronous system, I don't have these bounds. But as a result, I cannot time out. It's like when I'm downloading a page. I download and I see the hourglass and it's ticking. Do I wait a little bit more? Is the site really down or not? I'm not sure, yeah? So this is the challenge with asynchrony. So we have synchronous and asynchronous. We would like to live in an asynchronous world. Asynchrony is more realistic. Byzantine agreement, or the agreement problem, basically is that, think of a transaction. A transaction is executing on multiple sites. You want to make sure that all of them agree to commit it, to finish this transaction. So we say this is agreement. I want everybody to do something. I tell everybody do it. And I want to make sure that all of you do it in spite of failures. Yeah. If there are no failures, this is a trivial problem. But the problem is in spite of failures, including me failing. So what if I just sent a message to this group and not to them? We want to make sure that all of you, all the good ones among you, all the non-failed ones among you, listen to what I'm saying, even if I fail. So that's the problem. And then there are the failure modes. So I've been discussing crash failures, but also it is possible to have malicious. And in this context, often people use the term Byzantine because the original paper by Lamport talked about Byzantine failures and called it malicious. The story was developed as a Byzantine army problem. Now there are two very interesting and important results. One of them is that in a synchronous system, so one when you have timeouts, if you have malicious failures, assuming you have malicious failures, then you can only solve the problem if you have at most 1/3 faulty processes. So if more than 1/3 of you fail maliciously or lying and trying to do bad things, we cannot solve the problem. It's impossible to solve. But if it's less than 1/3, we can solve it. And there are protocols. Okay, so an impossibility means it's not possible. It would be stupid of me to ask you to try and do this as a homework assignment because we know it's impossible. The more complicated and more kind of important result is what's called the Fisher-Lynch-Patterson impossibility result, and that is even with crash failures in an asynchronous system. So now it's an asynchronous system, I cannot solve the problem. What does I cannot solve it mean? It means I cannot guarantee that I will terminate, that I have a protocol that will finish. So it's possible to try and do it. Often it will work, but sometimes the system will be running in a way that cannot guarantee that it will finish. There's a liveness problem. It cannot finish. So we have protocols that guarantee safety. We never do something bad, but I'm not guaranteed to terminate correctly. Okay, so this is like just some background information. So now we live in a cloud environment. What is a cloud? Cloud is lots of computers. This is like data center, Google data center. So there are lots of racks of computers, and they are not just any computers, they are commodity computers. What does commodity mean? It means just a computer that I can buy from the local store. What does this imply? It implies that it can fail easily. It's not a high-end computer. These are racks of lots of computers, and some of them are going to fail. So we have to design all the time with the notion of failures in mind. I also want to make sure that I can scale, because we're going to take all the data. Imagine this is Google or Amazon. I want to put all the data of the world. So this has to be huge. Yeah? I need to make sure that the data is going to be available and fault tolerant. And I want to make sure that the data is consistent. Nothing is wrong. Everything informally is consistent with each other. So let me try and give you some basic ideas of how to solve some of these problems. So let's first address scalability. So scalability is the problem that I have a lot, and let's focus on data. I have a lot of data. Much more than I can put on this computer. So what would you do? Yes, store it on multiple computers. Instead of on one computer, I'll have 10 computers. That's why I have a data center. So before data centers, before the cloud, people usually thought in a very different way. They said, if this computer is not big enough, throw it away and buy a bigger one. That's the scale-up solution. Here, with the cloud, we are looking at a scale-out solution. So I have more and more computers. And so if I have a lot of data, a lot of stuff that I want to store, what we're going to do, we're going to break it up. They cannot all fit on one machine. We're going to break it up into lots of pieces. So I put some of it on this computer, some of it on this computer, some of it on that computer. So that's the scale-out solution. Then there's the problem of consistency. Now I want to update my onions and my dresses. I bought two things. I went to the store and I bought both of these. And I obviously bought the two of them. So I want to make updates to both of them. So we need to have transactions. And like I said, a transaction is basically a bunch of read and writes. And you want to execute them in an atomic manner. So if you have Alice and Bob here, or Superman and Wonder Woman, and each of them have their own account, and Superman gave Wonder Woman some money, then it had better be that the account of Superman is subtracted by $100 and the account of Wonder Woman is increased by $100. Have you seen this problem before when we talk about transactions? So what are the protocols that we use to solve this problem to make sure that it's atomic, that even if there is multiple concurrent transactions, that they are still...
Mutual exclusion.
We need mutual exclusion, so that's an operating systems term. When it comes to a database term, we use concurrency control, which is kind of the same thing, but mutual exclusion typically assumes mutual exclusion, so it doesn't allow anybody, but with database world, we want reads to be concurrent, to be allowed, so we use concurrency control. So basically, we developed lots of protocols for that purpose. Now we have data that is going to be on different disks, and they're going to crash. So now Wonder Woman has her account there, and she wants to make sure that even if this computer is down, she can still access her money. So a standard approach to do fault tolerance is what's called replication. You have, instead of one copy, 3 copies. This is different from the partitioning. With partitioning, I had this data, I broke it up into pieces. With partitioning, I take this data and I replicate the same thing on multiple sites. And then I have to make sure that I update all of them, for example, and when I do a read, I read consistently. So that's all. This is what's called replica control. So we have concurrency control protocols, we have replica control protocols, we have recovery protocols, we have a whole bunch of protocols that have been designed for a long time and made the fundamental assumption that there's only crash failures. Okay, so all of this stuff was developed in a crash. So protocols traditionally have assumed crash, and I'm going to use this symbol. Whenever you see it, you know I'm talking about crash. So to achieve scalability and consistency, a very standard protocol that we have used is called two-phase commit protocols. They are commitment protocols. It's a protocol that guarantees that when I do this sharding, when I do this partitioning, when I break up data across different sites, I know that they all agree on the same thing. So that's a two-phase commit protocol. I'm going to give you a high-level description of it. For fault tolerance, we need to make sure that all the copies are consistent with each other. So we have various protocols. I'm going to use the distributed systems terminology here, and often they're called in the database world replication protocols. In the distributed systems world, they're called consensus protocols. And a very famous protocol for that is Paxos, another beautiful Greek island. You know where Paxos is, anybody? The real island? It's on the west coast of Greece. We still need to go there one day. So let me, these protocols are all for crash failures. So I'll just explain them again at a high level. So it's a consensus protocol for crash failures, and it's a very significant protocol. It's for asynchronous systems, so it works in an asynchronous world. What does this mean? It means it's not guaranteed to always terminate. It was developed again by Lamport, so Leslie Lamport developed a lot of these fundamental protocols that we are using. And the interesting thing about this protocol is it was developed, he developed it, and he was very excited about it, but he wrote it literally in Greek. The paper, if you go to the original paper, the Part-Time Parliament, it's in English, but full of Greek words. Maybe you'll understand it better. He has all these references. He has merchants going back and forth selling olive oil, and nobody understood what he was talking about. He was very disappointed in the community, and it's an interesting story. There's a blog where he writes how he ended up. He said, "Okay, forget it. you guys are not interested, I'm going to write it again. And he wrote it in computer science terms, like we write things very boring and stuff, and still nobody understood it. Eventually, almost 10 years later, so the paper was originally published in 1997, 98, maybe 97, and it took almost 10 years, 2006, Tushar Chandra at Google decided to implement the Google file system and to use Paxos to have a highly available protocol. And then Tushar gave this presentation, which was called Paxos Made Live, and explained how actually Paxos was taken and implemented in a real commercial system, large-scale commercial system. And it's still running now, and actually it's been a very big success. If Facebook, any of the distributed systems that you use now has underneath it some variation of Paxos or a broadcast protocol that is very similar to Paxos. So this is the latest thing was Spanner, which is also one of Google's latest big data management systems. So how does Paxos work? Paxos basically, there's a bunch of us who want to agree on a value. Just think of it like this. We all want to agree on a value. So the easiest thing with all these distributed protocols is to say, let's assume that there is a leader. If I'm sitting at the podium here, I'm the leader, I can control things. How am I chosen? There must be a system to choose me. Okay, this time Dimitrios picked me, but it could have been more democratically. How would you do it? Ask the whole group, and if there are different opinions, how are we going to decide who wins? Somebody else.
By voting.
By voting, and if you vote, who ends up winning? What's the word?
The majority.
A majority. So if you get a majority, if I get a majority, then my competitor is not going to get a majority. Yeah. So a majority means that I win and I got a majority of votes. So that's what we need to do. We need basically to have what's called the leader election protocol. So we have a leader election protocol. Once I become the leader, I'm going to decide I want to give a lecture. So I need to make sure that this value, this commitment, this whatever decision I have is made fault tolerant. How do I make it fault tolerant? It's actually, again, I give it to enough people that I know that it would survive, which is a majority of you. If I can get a majority of you to agree to what I want, then I'm going to know it's fault tolerant. So that's another. So the protocol keeps on using this idea of majority a lot. So but you don't need to know the details. What's important is there's a leader election, which depends on the majority. There's a fault tolerant phase, which also depends on the majority. And then once I've decided, once I know it's fault tolerant, then even if I fail, it doesn't matter because enough of you are up. And this protocol immediately is going to work the way I've described it if at most a minority fails. So at least a majority needs to survive. So if I have F failures, potential failures, I need to have 2 F plus 1 to survive, to be able to succeed. So that's basically the protocol. You have a leader election, fault tolerance, and then a broadcast at the very end. Let's look at another protocol, which I described, which is the atomic commitment or two-phase commit. Two-phase commit comes from the database world, so it looks very different. Again, it's under the crash. So we have a transaction that is being executed by lots of different individuals. So first we need to know whether all the nodes agree to commit the transaction or not. Some of you might say yes, some of you might say no. So instead of a leader election, typically in a transaction management system, we assume that the coordinator has been designated, like I was put here in front of you. You didn't have a voice in that, so I was just decided. But the first thing I need to do is to discover from you what is the value. What is it that you are interested in? So there's one phase of value discovery, and then I need to make it fault tolerant. This is the database world. The way we make, if you ask a database person, how do you make something fault tolerant, they will think of disk. We have what's called the acid properties, durability, and durability comes from disk. So typically what we do is we take the value, and once I put it on disk, I know it is safe. So that's the traditional way of doing fault tolerance. And then once it's made fault tolerant on disk, you announce it again. So you see there are similarities. So this was some work that we've been working on, exploring the relationship between these two different protocols. Now this protocol has a serious problem, and everybody in the database community is very aware of this. I'm not telling you anything new until now. It can block, meaning that if I get to know, I'm the leader, I got to know your value and then I failed, then you don't know, and I decided something, then you have a problem. You cannot continue. You cannot make progress until I wake up again. So that's called the blocking problem. And there's a variation on two-phase commit, which is not very popular because it's expensive, called three-phase commit, where you replicate the decision. How do you replicate it? You give it to a majority. So now we have value discovery. We replace the fault tolerance of putting on disk, which was quite fast, but results in blocking, with a distribution, making it fault tolerant by making enough people know about it, and then announcing the decision. Now you see the two protocols actually have lots of similarities, meaning Paxos and commitment. If we look at the three-phase commit protocol, it also has, what if the leader fails? They make sure it's non-blocking by electing the leader. So again, you have a leader election and discovery, and then fault tolerance, and then an announcement. So now we have two protocols that actually can match with each other, and this is what we ended up doing. We ended up observing that there is Paxos, there's three-phase commit. They're quite similar. In fact, they both need a leader election at different times. One of them requires a value discovery, but actually Paxos needs a value discovery, and it does that after the failure. If you go to the details of the protocol, if there's a failure of the leader, the new leader needs to discover if the old leader had gotten a value out or not. So actually, it's quite nice. And then you have the fault-tolerant case, and then you have the announcement. So what we did is we proposed a unification of these protocols, a framework, where you have leader election, value discovery, fault tolerance, and decision. And it is interesting because it helps us understand the protocols, but it also potentially helps us in developing new protocols. And we were able to develop a few new protocols that fit with this paradigm and solve different problems within this context. So there is three-phase commit, here it is, and there is Paxos, which here it is. So they're very similar except for a few details. Okay, I'm running out of time, but I started by telling you I want to talk about malicious failures. All this has been about crash failures. So I need to dig a little bit deeper into the problem of consensus to do this. So let's abstract things. Paxos. How does Paxos work? A primary, I'm elected, I'm the leader, I make a decision, and I make sure that enough of you know about it. Enough of you meaning a majority. So that's basic. So let's focus on this enough of you. Forget about the leader election. We need to elect a leader at any rate. So let's assume we have a leader election part. Let's just focus on the fault tolerance part. The protocol is centralized, meaning everything comes to me. You tell me, I tell you. So everything goes through this phase of communication, back and forth, back and forth. So it immediately means it's order n messages. If there are n of you, you need to send a message. If there are n, then it's order n messages. And we can tolerate crashes. Like I said, it's a majority-based protocol, so it can tolerate at most half of the sites. As a result, we have the quorums. If I have a majority, you cannot get a majority, because if you have a majority, there's going to be somebody in the middle, and this one person, this one node, in the worst case might fail, but it will not lie. So if I get a majority, you cannot get a majority because there's one in the middle, and the one in the middle cannot lie. It's crash. That's the whole idea of crash, is that if you fail, you just stop talking. You don't say something wrong. Now this is the challenge once I move to malicious behavior. The one in the middle could say different things, so I cannot live with the simple majority world. So we use majority quorums because I need an intersection of 1, and to tolerate failures, I need at least 2 C+1 if I assume at most C failures. Now, almost a year later, after Lamport developed his protocol, Bloodless Cough and one of her students, Miguel Castro, developed practical fault-tolerant Byzantine agreements. And that is a protocol that is designed for malicious failures. Again, it's interesting. These protocols were developed in the late 90s. Most of you were not born yet. Now they're very important, especially this one is getting significant importance. So it takes 20 years for the research that we are doing to actually see the fruition, which is, I think, important to realize, is that when these people were developing these protocols, it was interesting, it was speculative, but it wasn't practical. But now it is actually very practical. So now look at the top here. Yeah, so up to here this is Paxos, we have crash. I'm going to change it from crash to this symbol which says that I'm in a malicious world. So if you see this symbol, it means that I can lie. So this is not going to work. Like I said, quorums, majority 1 in the middle is not going to work. So, and worse, the leader could lie. So I might tell half of you something and the other half something else. This was the original Byzantine Agreement protocol, is that there was this Byzantine army that is going to attack a village, and there were generals, and some of them might lie. So some of them might say attack, and the other half withdraw. And then the army is split, and you lose. So we need to make the protocol more tolerant to these type of things. So the first thing they do is that you need to validate that what the leader is saying is actually consistent. So you need an extra phase. This is a very complicated protocol. I'm making it look simple here. It is not simple. But the basic idea is we need an extra phase to tolerate, in some sense, the failure that a leader could do. But then once I get it to you, so first I need another phase to verify what is being announced by the leader. But then once we add this phase, we also don't trust everybody in the room. You could also be lying. So everybody not only has to answer me, but they need to talk to each other. So the protocol, instead of linear, leader-based, it needs end-to-end communication. So we add a new phase and add n-square communication. So it's an expensive protocol, but it's a correct protocol. Yeah, so it's correct. I want to remind you, this is an asynchronous system, so it's safe, but might not terminate. In practical world, most of the time it finishes, so we live with it and we are happy with it. But it is possible that it might not. So in this world, we have at most M malicious failures. Now what we're going to do is we're going to require quorums, but instead of a majority, which has intersection of 1, we're going to require 2/3 sizes. So the size of the quorum is bigger. What does 2/3 guarantee? It guarantees that if I have an intersection, I will have an intersection of M plus 1. I will know that in the middle, if I have 4, I will have, and let's assume 1, at most 1 malicious faulty. So we designed the system assuming that there is at most 1. Then if these two answer the same thing, then it's correct. Because one of them might be lying, but the other one is not lying. So as long as I have M plus 1 in the intersection, I can have at most M faulty. If the intersection has M plus 1, then I know that, and they all say the same thing, attack or withdraw, commit or abort, they all say the same thing, then even if some of them are bad, it's okay. They are all consistent with each other, and there's at least one correct guy in the middle. Since there's at least one correct one in the middle, and they are all the same value, then it's fine. So as a result, we require quorums that are 2M plus 1 instead of M plus 1, so 2/3, and the intersection has to be big. So this is a correct protocol, but it's a complicated protocol. It's an expensive protocol in 3 different ways. We needed an extra round of communication, we needed N² communication, and we needed bigger quorums. Okay, so we've been working on this problem also, and what we were interested in is to say, okay, where are the expensive parts and why do I need this? The expensive part is usually that the leader is malicious. That's why we added this extra phase of communication in the middle. Okay, what is the typical situation in which one works? I will argue, it's not the only situation, but it's a reasonable one, is that the University of Cyprus has its own data center, but it doesn't have enough resources for everything it needs, for the fault tolerance it needs. So it's going to use some public cloud and some private cloud, some external and some internal. If you are in such a situation, then the internal is with people I know, I trust, we have a firewall, we've protected it. The rest is in Amazon land, I don't know what it is. Actually, I was at a workshop 2 days ago, and people argued exactly the opposite. They said, Amazon, I trust. They put in a lot of money. The local ones, I don't trust, because whatever, we don't trust the people we hire. I really don't care which model you want, but what's important is that there is a cloud or a set of entities where there's only crash, and there is the rest, which is going to be malicious. And now we are going to develop Paxos-like protocols, PBFT-like protocols, to help me solve the consensus problem in a more efficient way, by taking advantage of this different modes of failure. In the past, there have been various protocols which did hybrid protocols, but I believe our approach is the first where we know where the good guys are and the bad guys are. Where the good guys is not good, they just crash, yeah? So they are not going to lie. So some nodes are crash-only untrusted, some nodes are public, untrusted, and Byzantine. And we can benefit from both, and we have a protocol, Cmore, which we're going to present in the spring. So Cmore works in 2 modes. I'm just going to give you quickly what I'm talking about. And look, it works in crash and malicious. So I want you to just... So the primary, this was the big problem with PBFT, is that the primary can be not trusted. That resulted in this extra communication phase. So we're going to put the primary in the private cloud. And as a result, I'm going to save one round of communication. And rounds of communication is important because it's latency. It's basically one more out and back. Yeah, so it's the overhead. So the primary is going to be crash. The primary sends it out to everybody. Now some of it is crash and some of it is malicious, and the protocol can deal with that. It is order n because it's going to be still communicating with the primary, so it's in that sense it's quite efficient. At most m malicious false and at most c false, and we have bigger quorums because there might be malicious failures, so we still need a quorum size that is bigger. It's a function of both m and c, so 2m malicious and 1c for each of these. So it's kind of, it also, we have another mode of it where I don't want to put all the work on the primary. I will just use the primary to announce at the very beginning, and then we're going to have the rest of them communicate with each other. So I'm going to sacrifice the linear behavior. This is if you are interested in reducing the load on the private cloud, which is again.
If you allow me one question, so the quorums are considered to be the same level, but a lot of times, like also you mentioned spanner, and the data center architectures are very much hierarchical in a sense. So is there any work on these hierarchical quorums that takes into account its overlaps and?
So we haven't done this here. But yes, there is a lot of hierarchy. Actually, I strongly believe that you can do a lot of the spanner was developed for crash, but one could play around with parts of it being malicious, parts of it being crash, and collect the forms like this. So that's a very good. Yes, that's very possible. Here we were thinking of a flat world. This is following in the PDFT kind of approach. So we have a primary. The primary just sends it to everybody. It's still only crash, and then the rest of them communicate with each other. And so we might end up having, and mainly we don't want the private cloud to be involved, so we are going to have the extra penalty here of n-squared. Okay, so this is basically Cmore, and the question is how much time do I have?
Well, we have 10 more minutes.
10 more minutes. Okay, so I'm going to now jump into a very different world. I probably will not finish everything I want to say, but I'll give you some idea because I think it's very exciting. It's the world of blockchain and Bitcoin. So here, up till now, I've been talking about a well-understood universe where we know n. I can always say a majority. Once this lecture started, we closed the door. We all sat here. I can count you, and I know what n is. I can, as a result, know what half of you is, what the majority is. I can tell what is 2/3 of you, all of these things. But what if the door was open and some of you go and some of you come in and it's just dynamic? And this is the world of especially Bitcoin, where there is an environment and there are nodes, but we do not know who is in the system, who is outside of the system, how many are in the system, and how many are outside of the system. So that's an important thing. So the number of participants is not known. So all the consensus protocols that we've been talking about for the last 30 years do not help us solve this problem. And this is, in a way, for me, the intellectual challenge that Bitcoin posed to the distributed systems community in particular. Is what if you do not know n? So all the work we've been doing, assuming majority, is not there. All the work we've been doing, assuming 2/3 majority, we cannot use it. So what do we do in this world? And they did something. I do not necessarily like their implementation or their protocols, but this is what we have. So it's important for us to move forward to understand what has been done. So let me just briefly describe to you what is the story with blockchain. Traditional banks, think crash. You have a big bank, which is sitting in downtown Nicosia, and it's a big building with nice Greek columns. You trust it, you give it your money, you know it's going to be there. If I come back a month later, a year later, it's going to be there. And how do we transact with each other? I have my bank, you have your bank, and I want to give Dimitris some money. I write a check, I give it to him, he goes to his bank, the banks communicate with each other, and he gets my money. In fact, the banks probably do not send real money, $100. They just write down, we owe him $100, and then tomorrow his bank will owe my bank some money, and they're all just ledgers and money that is written on a log. And so this idea of a log or a ledger that captures the history is very important. So we have a bank, in this case, Bank of France, and Bitcoin says, we don't want it, we're going to have a revolution, and we're going to throw it away, and we're going to replace it with a peer-to-peer network. Everybody is going to be part of this. Instead of having this big one trusted third party, we're going to have everybody who wants is going to be part of it. Everybody's going to keep a replica of the entire history, of the ledger, of the log, and we're going to work like this. Notice, I don't know all of you. I don't trust everybody in the room. So we have to work on the assumption that there are people in the system that are not trusted, that actually want to cheat the system. So, how does Bitcoin work? It's the idea of a cryptocurrency. You have basically a way in which I am going to have a public a signature that I can only sign, but it's my private signature, but anybody has the corresponding public signature. There is a cryptographic technique called public key encryption, where basically you can do this. I can sign it, nobody knows my hidden secret, but anybody outside can verify that I actually signed it. So like when I go to the bank, if you take my signature, they look at it and they say, yes, this is an Abbadi signature. So if Alice has a Bitcoin, what she does is she associates with it the public key of Bob, so Bob's name, Bob's identity, and signs it using Alice. So Alice has the money. So Alice signs and sends it out to everybody. Now everybody knows that Alice gave to Bob the money, and there's the public key of Bob, so that's money belongs to Bob now, and there's the signature of Alice, which nobody can forge because this is a hard cryptographic problem. So now Bob has the money. What can Bob do? Bob can give it to Diana. How does he do it? He puts Diana's public signature, wraps it up, and signs it, and sends it out, and so on. So you end up having this chain, which is very nice because it gives us the history of every little piece of coin that I have in my pocket, where it came from. So if I have this money in my pocket, you do not know where I got it from. But if I'm in Bitcoin, you know that it came from him, and he got it from her, and so on. You know the entire history of this one coin. So it's not really exactly like real money, but it's close. And this works in an environment where there's untrustworthiness because of these signatures. And the signatures cannot be forced. That's the assumption. There is always an underlying assumption. And here it is that the signatures cannot be forged. So what is the blockchain? The blockchain is now going to be, I'm going to have blocks of transaction, a block, And that block is going to have a bunch of these transactions. Alice giving to Bob, Bob giving to Diana, etc. You all know what a linked list is? Okay, so a blockchain is a linked list. Basically, instead of every node having one value, it has a bunch of transactions. And so we have a linked list where we have pointers to each other. Now the problem is that what if somebody takes some of this and changes it? You know, we don't trust anybody, so somebody could change it. So how do we get around this? We complicate the pointers. Instead of just having regular pointers, do you know what hashing is? Okay, so hashing is you have something and you put it through a function so that in one way it's easy to solve, in the other direction it's hard to solve. So if I give you the answer to the hash, it's very hard to come up with the original thing. But if I have the value, you can hash it. So what we're going to do is, in addition to a pointer, we're going to have a hash. So this one is going to have a hash of this. This is going to have a hash of this. So if somebody changes it, then if I hash this block, I will get a value that's different from the hash that is stored here. And so we can detect that somebody was trying to cheat us. I'm going very quickly, but basically this is the basic idea. So now when somebody wants to, so now this is a linked list. What is the most important operation? I'll have to stop, but what is the most important operation when you have a linked list? Is you want to add something. So to add a new block, but we have lots of copies of this. Everybody has a copy of this blockchain, of this linked list. So now we have to agree with each other who's going to add the next head of the block. This is a problem, but I've solved this problem. It's the consensus problem. So can I use the consensus? Well, I cannot really. I can use the consensus if I know the number of people in the room. So if I am in what's called the permissioned blockchain, which is different from the cryptocurrency, then I can do PBFT, Liskow's practical Byzantine Agreement protocol, and tolerate a certain number of failures. However, in the crypto world, I cannot communicate because I don't know N. So then they do what's called mining. Mining is basically trying to solve a cryptographic puzzle, a hard problem that with very high probability, I'll be the only one that solves it, given a certain amount of time. So we use mining to solve the consensus problem.
So the permissionless blockchains still rely on, because mining has been one of the big problems of also Bitcoin is wasting enormous amounts of energy just to have all these GPUs working to solve puzzles. It's like a nonsense puzzle solving game just for the product to be operational. So it's still, is it still a thing that permissionless blockchains will?
So that's a very good question. It requires a long answer. So the answer is yes and no. So the cryptocurrencies that are around, Bitcoin still uses mining. Ethereum uses a different approach, which is proof of stake. So this is called proof of work. They use the proof of stake, which also has its own issues. It basically makes the rich person be able to become the leader and hence do the consensus. There's a whole bunch of academic work which is trying to solve the leader election problem or the consensus problem in an unknown number by creating what are called committees. You create the committees using basically randomization on a very, and one good example of this is a system called Algorand, which Silvio Micali is proposing. They have also a startup which is trying to do this. All of these are still in the exploratory phases. I think I'm going to stop here. But I want to make sure that well, the message I'm trying to get at is that there are basic issues that we need to address in a new world that is looking a little bit different from what we were used to. Instead of having just crash failures, especially for a database person, we were very comfortable with this notion of crash. There is a problem if I start dealing with untrusted hardware and unknown number of participants. Unknown number of participants also poses us lots of interesting problems. So we are rethinking a lot of